Good evening. How are you doing? First of all, welcome to the Big Things Meetup. Today we'll have Robert and David, who will be talking a lot about stream processing. And first of all, I would like to introduce Phil from Proofpoint, and thank you very much for the kind hospitality. I will say two things. One, pizzas are arriving. Okay? So be aware, food is on the way. This is one. And there are giveaways by Proofpoint, thank you again, when you leave. So don't forget that. And I'll give you at the stage if you. Thank you.
Thank you very much. First of all, thank you Danny for and big thanks for arranging this meetup, and big thanks for where is Amit? Here. Amit Buzz for contacting Robert and David and asking them to come. So big thanks to them. I'll talk very shortly because pizzas are coming. And so why are we here? So Proofpoint is a cyber company. You probably know that. So it's a strong, the fifth biggest cyber company in the world. But why are we here? So one of the things we're doing is at Proofpoint is we're doing SAS protections, which means the old perimeter of I have a firewall and everything is inside. It's it's the end. It's the old world, and everything is moving to SaaS, the cloud. Your employees could be anywhere, your data and files can be anywhere, and what we're doing here is we're protecting them. And why is it connected to stream processing? Because what we do is connect to your real SaaS applications, which poses an interesting engineering problem called stream processing. So if you connect to your Google Drive and your Office 365 and you have a few tens of employees, few tens of thousands of employees, sorry, and few tens of millions of files. So how do you collect all this data in real time? And we're not talking about small clients. Proofpoint protects 55 of the biggest 100 companies in the world, like we're doing name dropping, so Apple, Citibank, etc., etc. So collecting all this data in real time is an interesting thing to do. Now, connect that with the story of a startup that was acquired a year ago, meeting one of the companies that sell the best in the world for cyber, and you have a scale of about twice per month. So that means 10 months ago we have 1/1000th of the amount of data and events we have now, and we keep scaling in probably the same rate. So a lot of engineering problems, and stream processing is not an old technologies realm. So we have a lot of interesting problems in terms of handling this scale, and this is why we have Robert Metzger from Data Artisans and Flink, and David Ostrovsky from Couchbase, because we're using Flink and Kafka for event processing, and we're using Couchbase and Elastic for our databases. So we said we'll bring two of these very distinguished engineers to talk about stream processing. And of course, I'm telling you that we have the brains, now we need the people. So of course we're hiring, and if you know of anyone that's interested in scaling up twice a month, so please spread the word, and we're very interested. So without further ado, please welcome David. Yeah. Start. David is
Hi guys. Alright, so I'm David, I'm a solution architect at Couchbase.
Only one thing.
Yep.
Just try here maybe.
Oh, we're okay. I'm gonna go back there because sorry. No, I'm good. I have like 2 slides. I don't need to. We'll talk half an hour about one and then half an hour about the other. Alright. Because I don't like slides. So let's talk about stream processing. Right, this is why we're here, and as the nature of my job dictates, I go to a lot of customers. I see a lot of different data processing setups, and even though there's like 500 companies here just in New York City doing a bunch of different things, internally, if you look at how they're handling data, there's a lot of similarity, right? If you take a company like Proofpoint or a company like whatever, Seismic, which does something entirely different business-wise, internally they have a lot of very same issues with bringing in data, processing it, handling latency, handling scale. So you keep seeing the same set of tools repeated across different companies. And in every step of this process, there's several choices you can make. And it's very interesting to see what those choices actually affect. So for example, you can pick one of several databases, and you can pick one of several stream processing frameworks, but ultimately what you end up building with them looks very similar, even though there are different products involved, right? So what we want to do is talk about databases in a stream processing context, right? And I'm not talking about SQL Server or Oracle. Obviously it's kind of boring, because you take data from SQL Server, you write to it. It's not important. I'm not saying it's not important, but it's not very interesting technology-wise and scaling-wise, right? So we're going to be talking about specifically NoSQL databases. Now, NoSQL is a buzzword which has basically no meaning. So in this context, what I'm talking about is large distributed databases optimized for scale. Obviously, I work for Couchbase, so I'm including Couchbase in this, but pretty much anything I say can be applied to most databases, right? So if you hear Couchbase, or we see an example with Couchbase, you can map that to Cassandra or Mongo or whatever, or HBase, because a lot of the things will be pretty much similar. Right? I'm going to be talking about mostly high-level concepts, not so much about specifically things you can do with a particular tool, right? And so when I say you can do this with Storm or Flink or Spark Streaming, it's going to be more or less the same thing again, right? So what do you do with a database? Where can you, and why would you even use a database in a stream processing context? Obviously, right, how many people have read the blog about turning your database inside out from Confluent? There's like three, four people, right? It's a very cool blog, and it describes how you can get rid of databases and only use Kafka for everything, which is an awesome concept, but in practice, it doesn't really quite work out this way, because ultimately you still want to put your data somewhere and have it persistent and queryable, and most people kind of like databases for that kind of thing. So ultimately, there's only a few places in this process where it makes sense to use a database, right? And it's not like a trick question, right? But where can you put a database? You can put it as a data source, you can put it as a data sink, right? And you can put it somewhere in the middle where you go to the database back and forth in the middle of your data streaming process, right? And it does different things in every one of these spots, and we'll talk about what you can actually do with them in every place, right? So let's talk about because there's really very little alternative, right? For a database, one, you need to persist data and have it available in many different formats or many different ways of querying, right? So let's talk about the straightforward use case where you have the database as the sink, right? So you have a bunch of data coming in from somewhere. I'm assuming everyone's using some kind of streaming topology, right? So you have a bunch of either events coming in, or users clicking on ads, or interacting with ads, or whatever. You have a web crawler crawling web pages and pushing them in. But ultimately, all this bunch of mobile apps, whatever, I can give examples all day. But you have a bunch of events streaming in, and they flow into some kind of streaming topology. It's almost universally some kind of message queue, so Kafka, Kinesis, something, right? Then you have your whole processing topology. It does a bunch of stuff. And eventually, you have a product, right? You have your data processing system does something, and you get some kind of either an enriched event or some new data you discovered, or maybe a machine learning model you trained and you want to save it, or you're building profiles about users, whatever. You end up with something, and this final product needs to be saved somewhere and then made available to the actual system which makes money for your company, right? So a web UI that shows a pretty dashboard. That's like 90% of all companies do a lot of big data stuff, and it ends up as a dashboard with 3 graphs. So this makes the most sense, right? And in this case, it's very straightforward of how you actually interact with the database in the stream processing. You do all of your data processing, and then finally you have either you use the native SDK for the database to just write records to the database, or you maybe have a connector, for example. Every database I named, right, so Mongo, Couchbase, Cassandra, HBase, every one of them has a connector for Kafka, connector for Spark Streaming. They have community support, for example, for Flink syncs, and there's a bunch of other things which you pretty much just push data into it, and it ultimately pushes the data into the database. Right, in this part, there's only a few interesting things we can talk about here, right? First of all, it needs to scale really well. It doesn't necessarily have to have low latency because writes are usually not latency sensitive. Because when you're talking about the database as the final resting place of your data, right, where it ends up, latency is not a big concern. Throughput is a big concern. Because when you have to process, whatever, 10 billion events per day, that's what 120 events per second. You need a database which can actually do 120,000 writes per second, or something close to that. And so this very quickly limits the number of databases you can actually consider. Right? This pretty much brings us to, again, Couchbase, Cassandra, HBase, ScyllaDB, because it's basically Cassandra, and there's 2 or 3 others which have that kind of throughput, and which are not super niche, right? How many people know the website dbengines.com? Obviously you know, right? So if you go, it's kind of like a popularity contest between databases, right? And they do aggregation of stats from Stack Overflow, Google Trends, and a few other things, and they give you rankings for different database popularity, basically, right? And so if you go there and you look at the top 10 databases, top 20 databases, those are basically databases you might end up using. So you'll have all the regular things. The first top 3 would be SQL Server, Oracle, and whatever, Postgres, MySQL. Then you have Mongo, Cassandra, Elasticsearch, obviously, arguably not necessarily a database, but very popular nonetheless, and a few others, right? And so in this use case, the important things here to remember are you do all of your data processing before the data reaches your database. There's a few issues with that, right? First of all, your data is oftentimes vulnerable on the way to the database, right? So especially if your events are not reliable, so it's not the data source where your events are coming from cannot retransmit the data. For example, it's a user looking at an ad. He's not going to go back and look at the ad another time if you lost the event somewhere along the way, right? And if it's whatever, a user doing something in the UI and they click save and this goes into your streaming topology, you can't go back and ask the user to refill the entire form in the UI and do it again. So there are a few important things here. One, your topology has to be very reliable, which is why almost universally someone puts a data store before the data topology, then does all the processing, and then a database at the end, right? This data store, in most cases, would be Kafka, right? Everyone knows Apache Kafka, of course. But if you're on AWS, Kinesis would be a close second. And there's a few others, right? RabbitMQ, whatever. It depends on what kind of skill you want to get. But the important part is storing the data and persisting it as quickly as possible so you don't lose it along the way. Almost every system I looked at which didn't start by persisting data and just injected it into some kind of data processing topology has data integrity issues, right? You always lose data along the way, nodes die, stuff happens. If your only persistence is going to be at the end of the data stream, you're going to have issues with data integrity and data persistence all somewhere along the way. Which brings us to the second place you can put a database. You can put a database at the beginning of your data stream topology, right? It doesn't have to be Kafka, for example. You can just put all of your data first into the database so it's safe and persisted, and presumably it's the same amount of data as it will be at the end, so it obviously will perform and scale to those levels. And it's probably going to be slightly faster, so that the time window of data loss is going to be slightly smaller if you go and write to a database as opposed to putting it, let's say, to Kinesis or Kafka. Kafka and Kinesis have a bit of latency on the ingestion part. We're looking, not a lot, like we're looking 10 milliseconds versus 1 millisecond. But even those extra 9 milliseconds sometimes cost money, right? So this is one reason you consider putting a database really at the start of your ingestion pipeline. But then obviously the question becomes, how do you get it out again? Right? And this is where the fact that all the databases we're talking about are distributed, scalable databases comes in. Every distributed database starts out with the assumption that it needs to be replicated, right? Replication and support for actually replicating data is an afterthought in most older relational databases, right? Trying to get your data out of Oracle or out of SQL Server without, Informatica or something, actually streaming data out as it changes from Oracle is a massive pain in the ass. Right? You either end up paying for Golden Gate, which costs more than the database itself, or whatever, writing some weird patch stuff, right? Or you go and you try to parse the commit log, and if you're using MySQL, there's a library, there's one Java library that everyone knows which parses the commit log. As I said, it's a pain in the ass. because all those databases started out 50 years ago, 40 years ago, and they never concerned themselves with actually streaming and handling data. Conversely, every modern distributed database starts out with solving the core issue of how do you replicate data, first of all, internally, right? So for example, Couchbase, because I know how we built it, right, started out with some hacky internal protocol for streaming data between nodes, because every node holds the replica of data from a different node. We had some kind of hacky protocol which was not exposed to anyone, and the first thing the customers did, well, PayPal in this case, was write a library which connected to a replication model and pulled data out, right? It doesn't matter if you want to hide your replication, someone will connect to the replication port and try to pull data out. Because customers really, really hate having their data locked in a database, and database vendors really, really hate letting customers get data out of their database. Right? This is the reason, by the way, why a lot of database vendors, not just Couchbase, were very resistant to add to exposing some kind of connectivity which streams data out of the database in real time, right? Any product person I talked to in Couchbase about event notifications or streaming connections, stuff like that, was initially very skeptical about it because we finally got the data from the user. Why would we give it back, right? But no, ultimately, everyone realized that customers really want the ability to get the data and stream it out, which is why every database in existence that's in the top 20 in DB engines has some kind of facility for connecting a streaming framework and reading events from the database as they come in, right? Couchbase have rebuilt entirely their replication engine, and now it's an officially supported component. You can connect to the database as just another replica in the cluster and listen to replicas in real time. Mongo have the upload, which is very easy to connect to and read with some caveats. You shouldn't skip too many events because it will roll over, but ultimately you can connect to the upload. Cassandra have the thing, every database, every major NoSQL database has a way of getting events in real time from the database as a stream. And the only reason that's possible is because they started out with the assumption that this is going to be a necessity in the database. Right? And so you connect to the database, you stream the data out, and then you can go and do whatever data processing you want to do. And ultimately, you usually end up streaming the data back into the same database, enriching it and whatever. Yeah.
When you say streaming data out of the database, you mean only listening it in real time as it goes in, or you can watch the entire data as a historical stream from the beginning in all sorts of data?
This is an excellent question, right? Because there are two entirely different use cases. I'll repeat it, right? So when we talk about streaming data out, is it just listening to events in real time as they happen, or can we just connect to the database and backfill the whole database out of it, right? Eventually stream the whole database out, and then maybe continue from the real time, right? Usually there's no difference. Almost every implementation, except for Mongo upload, because if it rolls over, it's done. Every other implementation basically lets you stream from the beginning of time until now, and then continue from now and later. Right, the only exception here from the big databases is Mongo, where you have the upload and you only have like a few events going back, let's say an hour of events back. And if you want to stream, you have to first backfill and then continue from the upload forward, which is it's a little annoying, but it's not that big. It's not that big of a deal. So yeah, so for example, in Couchbase, because the way to stream from data from it is the same replication protocol that it uses internally. It natively supports connecting to a node, streaming all the data out, because that's how we create replicas internally. Right? So if you add a new node, it will go and it will stream data from all the other nodes. And that's the same replication protocol you can connect to. Right? So in this case, this makes sense. And again, I'm not saying put a database at the start of your data stream topology, right? A database is not a replacement for Apache Kafka, and Kafka is not a replacement for database. They do very different things. The primary difference is a database holds the latest snapshot of your data, whereas something like an event log will hold the entire event log, assuming a certain compaction policy or a certain retention policy. But you get all of your logs. So if you have the same key repeated several times, you get it several times from Kafka. You only get the latest snapshot if you stream it from a database. This is the key difference, right? This is why a database isn't a message broker and vice versa. So they do address different use cases. In the case of a database, it's possible that you don't care about all the older values. You just want the latest value. In that case, it's perfectly fine, and you'll probably get it faster from a database. If you do care about older values, if you want the entire commit load, then you pretty much have to use a database which supports that. Which is, sorry, a data store, which is basically Kafka or Kinesis or one of the queues. Right. And so, here we get to the last and the most interesting use case, which is using a database in the middle of your processing topology. Right? This is the main part of what we're going to talk about. There are a lot of things you can do with a database in the middle of your topology. A lot of them are very dangerous. Right? So the straightforward case is you get an event, you want to enrich it. How do you enrich the event? You go to some external data store, you get some data, you attach it to your event, and it continues downstream in your topology and gets processed. What's the biggest issue with this scenario? Is that a trick question? Sorry?
Latency.
Latency, yes. As I said, not a trick question. I only ask very simple questions. Because I'm sure someone will say yes. Yeah, latency is obviously the biggest problem, and the more latency you have, the more parallelism you have to build into your topology to overcome the latency if you want to maintain throughput. It's not an insurmountable issue, but it's a big issue, right? Which again, very sharply decreases the number of databases we can even consider if we want to be able to enrich data from a database in real time as part of the topology. Yeah.
What about if the latency is because the enriching data is late arriving? Like
That's a very big difference. If your data is out of order and it arrives later, that's a big issue, right?
No, not technically out of order. For example, you have user clicking on ads, and only a few minutes later they log in, and you want this login associated with all the events.
This is an easier one, right? Because this, you can assume that your topology starts only after the session completes, if you can eat the latency. And then this is the same use case we talked about earlier, where your event actually, your topology starts in the database, right? And for example, this is basically what the guys at Seismic did with sessions, right? So yeah, you have to wait until the session finishes, and then you can process it. If you have to do out-of-order processing or some kind of latency, it's a giant pain in the ass, and don't do it. But if you have to, it's hard to solve. Alright, so yeah, so enriching, and the opposite of that, obviously, is building some kind of state. So you do your topology, in the middle you have some interesting information which you want to put in a database. For example, you're building a user profile, right? Your user goes and clicks on ads. I keep going back to that example because like half the room I think does ad tech, and the other does cybersecurity. Next time we'll just have separate sections. Sorry, one person from a bank. Fair enough. You'll have a section all to yourself. You build your user profile, right? And you do a bunch of important things. And in the middle, you also want to update the user profile and add the preference for cats. And next time you can show them ads for cats. And so your topology will have a side effect. Now, when I say side effect, I mean that in the functional programming sense, right? How many people know a bit about functional programming? Everyone, excellent. Right, so the ideal topology, right, is built entirely with pure functions. Right? What's a pure function? Who can tell me? No side effects, thank you, very much. So ideally, you want all of your functions in your topology to have no side effects. It's wonderful, there's no bugs, and everyone gets a raise. But in the real world, no. Usually operators in topology have side effects. They either bring data in or they write data out. And as soon as you do side effects, you pretty much throw out all the delivery guarantees that the streaming framework provides, right? So when you go to a streaming database framework and you read about it in the documentation, it says, we support at most once delivery and we support at least once delivery. And some of the more advanced ones, like Flink, support exactly once delivery, right? Or Kafka or whoever, right? And that's wonderful. But the thing is, they only support it within the topology itself. As soon as you start putting data out, as soon as you have side effects, it supports nothing, right? It's all in your head. You're shaking your head, yeah, but as soon as you start writing to a database, it's the responsibility of the person implementing the application to actually provide the delivery guarantees. I'm being obviously glib, right? But the reality is, yes, the framework can promise what it actually controls, obviously, which is the delivery of messages within the framework. And as soon as you step out of that, you have side effects. You have to provide the guarantees for delivery, and this pretty much controls what you can do and what you should do with side effects in the middle of a topology. So let's look at some examples, right? Because I don't want to bore you with the 2 slides I had. So let's look at examples. I'm going to build a notional data processing pipeline. It's going to use everyone's favorite example. We're going to stream tweets from the internet. We're going to do stuff with them, and we're going to, everyone uses it, because where else are you going to get streaming data? So we're going to stream tweets from the internet. We're going to do some processing from them, right? And we'll talk about every choice in this topology and what you can do in this place, right? So first thing we have to do is let's bring tweets in, right? Because there's two ways we can go about it. Data can come to us, or we can go and we can pull data from somewhere. So in this case, we're pulling data from an unreliable source, right? Because you cannot go back and reread the same tweets. There's no API in the Twitter Firehouse to go back and reread them. There is, it's expensive, and I can't access it because I didn't pay. So we're treating it as an unreliable source, right? Once you get the data, what do you do with it? The first thing we want to do is persist it as quickly as possible. There is a choice at this point whether you want to process the data before you put it in the database, or put it in storage as soon as possible and then do the post-processing. It's a question of whether you want, again, if you're going to put it in a database, there are two trade-offs. One, if you do validation of the data, you get cleaner data in the database. You will have less data integrity problems. It will be, you won't have to go and do some post-processing on the database. I don't like putting junk in my database, so it makes sense. On the other hand, the more post-processing you do, the less raw data you end up storing, and the more latency you have, and the more events you might reject. Also, if you make a mistake and you want to change the way you pre-process data, you can't go back, because you lost those events. It's an unreliable source. Right, this is why, for example, in almost every case, it makes more sense to put raw data into some kind of event bus, Kafka, Kinesis, whatever, and then post-process from that, and then actually filter and put the stuff in the database after the post-processing. But first you persist it, and you persist raw events as much as possible into some kind of message bus. Right, so let's do that. We have a very simple Spark streaming application. Why Spark streaming? Mostly because I like, so it's interesting, right? It doesn't have to be sort of streaming or anything. Also, I want to show off the connector for Couchbase Restore. Right, so we go to the standard Twitter utils library that comes with every Spark streaming demo, and we stream a bunch of tweets from the internet. And here we can do two things. This is by the way on my GitHub. If you want to actually look at it later, you don't have to read the code right now. It's bad, but it does two things. One, it does some pre-aggregating of data and it puts it in one table in the database, bucket in the case of Couchbase, and then it takes raw tweets, cleans up the schema very slightly, and puts it in a different bucket in Couchbase, right? And that's our raw data. So then we have both cases, right? We do some pre-aggregation, so it's actually data that's ready to be consumed. And in this case, it makes sense because we're building sliding windows of data, and if we lose a window, like if you lose a few seconds, it's no big deal because in our case it's a statistical application which just does some aggregations. And in the other case, we persist as quickly as possible because we want to save the raw tweets and not lose them, right? And of course, you can improve this in all kinds of ways because it's a very unreliable application. So we'll run this and we'll end up with a bunch of tweets from the internet. And it's always a question of how you can actually filter them because you want to get enough tweets. So usually I go with politics. You can't go wrong with politics if you want lots of tweets. Please don't read them, they're terrible tweets. So this goes into our database. We can go and we can look at the database and see that indeed we are getting some tweets. Add some built-in buckets, and we can see that we're getting some kind of tweets with stuff in them, right? This is there, right? So this is actually an older. What we see here is this, right? So this is the raw tweet. Now we want to go and we want to do some processing, right? Let's do some natural language processing and do sentiment analysis because what do you do with tweets on the internet? Of course you do sentiment analysis, right? That's what everybody does. It's practically worthless because there's not enough text to actually do something meaningful, but it's a cool demo nonetheless, right? So how do we do this, right? There's several ways. One, I can query it. Querying is usually a bad way of getting data out of the database. Almost all query engines in every NoSQL database assume you're going to query a small data set. right? You can't yank out 100 million objects from database with a query, it's gonna choke and die. So this is true for Couchbase, Cassandra, Mongo, pretty much any database you want to talk about. Right, so querying is out. Querying is not interesting. We'll get to querying a bit later. So what do? We need to actually replicate it somehow, and this is where we go back to actually using the replication support built into the database to replicate this data out into our data streaming topology. For Couchbase, it's very simple. We have a client library in Java, which just provides events at a time. We can tell it to either start from the current timestamp or go back and backfill the entire database. Internally, by the way, Couchbase works very much like Kafka. Everyone knows how Kafka works more or less with topics and partitions, right? And you can parallelize all the partitions. In Couchbase, it works pretty much the same way, except it's buckets and vbuckets, virtual buckets. But every vbucket is almost identical to a partition in Kafka, in the sense that every object inside of it has a serial number, right? And you can stream them sequentially in the order of arrival within that partition. Right, so we can create a bunch of streams, exactly as you would with Kafka, and you stream every partition in parallel, and you get a bunch of data. Right, and they come in order of adding to them. Right, so if we look at the way it works, is it's a very simple interface for the library. All we do is subscribe to the data event. Right, this is part of the SDK. It's not the Couchbase SDK, which does regular key value commands. There's a separate SDK for TCP streaming. It has exactly 3 events, one for data events, one for control events, and one for system events. Every time we get a data event is when something changes. So a document was added, deleted, changed, stuff like that. Right. And so for every document, for every event, we store it in a queue. In this case, this is a Storm implementation. The implementation, for example, for Flink would be almost identical. Right. It would be in order to support back pressure, we have an internal queue within our source, right? In this case, a spout in Storm. It has an internal queue. It reads a certain amount of items from Couchbase, puts them into a blocking queue, and then every time the topology goes to the source and says, give me another tuple, or give me another event, it puts the event out from the internal queue, and then a new event joins the internal queue because it unblocks one item. Right? It's slightly different in Flink. You probably wouldn't do it like this, but in Storm, that's pretty much the standard way it works.
In Flink is the ready to use connector for this?
No, but you can take this, copy paste, change 2 libraries, and it'll work exactly the same. Not just that, I think you have like an adapter for Storm topologies in Flink, right? So you can pretty much run this as a bolt or as a spout almost natively. I wouldn't do it. I'd still write it natively for Flink because it's like really 3 lines of code to change in 2 lines. But it's a very simple API. You just get events as they come in. You look at what kind of event is it. Is it a new document or a deleted document? And then you push it downstream. Right? And what we do is we have a very simple topology in Storm. But again, you can take this and load it up into Heron. You can load it up into Flink. Any event at a time system that you care to name. I'm specifically not saying Spark Streaming, because Spark Streaming is very different. It's not actually a stream processing framework. It's micro batches, and it kind of pretends to be streaming, but it's not. And there it's entirely different. You don't do event at a time. But, you know. All right, so what we do is we have a spout, which is the source of our items coming in. It's listening to Couchbase. It's listening for new events being added in the background from the application that brings in tweets and writes into the database. From there, we send it to a bolt which filters out all the events we don't care about. So deletions we don't care about, explorations we don't care about, just new documents. From there, we can send it to a bolt that does sentiment analysis. Right, this is a very trivial sentiment analysis. I'm using the Stanford NLP library, which you feed it to text and it gives you an integer between 0 and 4, 0 being very negative and 4 being very positive. And then we take this integer, we add it to the JSON, and we write it back into Couchbase. Right? This is a bad pattern in at least 3 different ways. Right? And doing it on purpose. First of all, if you write an event, an updated event to Couchbase, it means you're going to end up getting it again in your streaming topology. And this time it's change the document rather than a new document, but you will get it again. and then you have to look at it, see that it's already changed, and discard it. It's terribly inefficient. There definitely are better ways to do it, but not in. But it's. I did whatever was quick and dirty, and that's how you do it in the startup, obviously. Also, this is. This has implications for data integrity because you have essentially two streams: one writing to a database, and one listening to it, changing something, and writing back to the database. They have very different performance characteristics, right? One of them is very fast, it works as fast as the database can write data. The other bottlenecks on CPU for the language processing stuff, right? So the slow part isn't reading from the database, it's actually doing the processing, right? They scale differently, they shouldn't be part of the same streaming topology. They should be treated very differently. And also, I'm doing a lot of extra work here, and I probably should just write the sentiments to a separate bucket or a separate document or something. But okay, so just for an example, we're doing this. So it goes to a bolt which prints out the message, and then finally another bolt which just writes to Couchbase. So reading here is using the replication mechanism. Writing is with a very simple Couchbase SDK. It's the same as you would from any Java application. You just open a connection to the database, you write the document to the database. You don't need a separate special connector to sync into Couchbase because it's a straightforward operation, just writing a document into it. Right? That's why for most applications, the source connector is usually pretty complicated because you have to provide guarantees. It has to be parallelizable. And the sync connector is usually very simple. It's just a small wrapper on top of their normal SDK. This is true for Cassandra, for example. The Cassandra sync for Storm is just a wrapper on the normal driver. Same with Mongo, same with Couchbase, pretty much everything. Because writing to a database is much easier than streaming from it. Okay, so if we run this, it will spin up and it will actually start slowly chewing through all the tweets. It will never catch up to the head of the stream. Right, because I'm bringing tweets in much faster than this laptop can actually do language processing on the tweets. Right, and so in reality, I have to have a much bigger Storm cluster to actually catch up to my very small topology which brings in data. Right, but it's doing stuff. We can actually go and see that it's processing about something like 5 messages per second. Let's take a look at this. Yeah, it's very few. It's writing like about 20 messages per second in small batches, right? Whereas we'll get easily several hundred tweets per second if you just write them in. Right. So this will continue, and in the meantime, we can take advantage of the fact that it's a database. We can actually query data, right? So we can either go to the UI and query for stuff. So we can go and select some tweets, right? And we can go and use the regular query, select from, where sentiment to that, right? And this is just regular database stuff. Every database has some way to query it. This would be identical in CQL and Cassandra. This would be slightly different in Mongo, but it's pretty much all the same. But now, let's talk about how else you can get data out from your database and use it in interesting ways, right? So what if I want to just get the good tweets out of my database? I don't want all the tweets. I don't want to read all the terrible things people are going to tweet about the stock, as if anyone would tweet about it. I just want the positive stuff, right? So there's two ways. What are two general ways? What are two ways we can do this? Seriously asking a question here, not a rhetorical question at all. Anybody is welcome to answer. Very easy question.
Go for the analysis and we stream it out whatever is passes the
yes,
filtration.
Exactly so.
The other way is to write to the database and then read whatever passes.
Exactly correct. Those are the two ways. There's really no other way to do it. So let's take a look at two of them. Right. So the first way would be let's stop. There's too many ways. Let's stop. So the first way is to just stream all the data out. Right. We ignore the fact that it's a database. As far as we're concerned, it's just an HDFS file. Right. We yank all the data out. We use our data processing framework to look through all the data, get the ones we want, discard all the rest. Right. This is obviously very wasteful, but it's very easy to do. Right. It's very easy because we already have the capacity for that. in this case, I'm using Spark Streaming just to demonstrate that you can do that with any kind of framework, because internally they will all use the same SDK, which replicates data from Couchbase. So you can use Spark, you can use Flink, you can use Storm, whatever, or Kafka. Right, so in this case, what we do is create a Couchbase stream. We filter out only mutations which have a field called sentiment score greater greater or equal to 3. Right, so only positive and very positive tweets. And then we can count them or can print them or something. Right? And so we do filtering here. Now this will actually work very fast. Right? Obviously, because the replication port is naturally very fast. It's designed to replicate the entire bucket to another replica. So going back there is going to read it as quickly as you have, if you have all of it in memory. So at memory speed, if some is on disk, it will do whatever it can from memory and then get the rest from disk. It will load everything into memory in Spark. Obviously, you're going to waste a bunch of memory and do a bunch of memory collection, but this works really easily. Right? And there's support for Spark SQL, but okay. So what's the other way? It's actually to push down the predicates into the database. Let's actually use the database as it's meant to be used. We'll do a query. So by the way, if we run this, let's see if this actually runs. Right, so let's update a few tweets. Okay, that's going to be an issue. Right, let's give a few of them a high score. Boom, so now this changed a bunch of tweets all at once, which means that now we got a stream of tweets coming in. Right? We didn't have any positive tweets before, that's why it was empty. Right? There are no positive tweets on the internet, they were all very negative, and so I had to create a few positive ones. So there we go, we have a bunch of tweets stream in, and now they're very positive, we can see them. Excellent. But this means that we got all of them, which is kind of inefficient. Alright, so what's the other way? The benefit of this is we don't need to pull, we don't need to run queries. This works continuously. So every time a tweet comes in, we listen to it, we filter, we get all the ones we want immediately. So that should be in real time. The alternative, of course, as you said correctly, is to query it. Right? And so when you query, you're just going to be using the normal database SDK to send the query to the database. It has some nice wrappers around it, and for the Spark connector, it will create an RDD out of it, or a Spark data frame, so you can do some Spark SQL stuff with it. But it's all syntactic sugar on top of basically sending queries to the database, getting a bunch of results from it. Right? So the advantage, of course, is you can do proper database stuff, so you can do a select. If you have an index and sentiment score, it's going to use the index, it's going to be much faster. But this would go back to the fact that databases aren't designed to return a lot of data from queries. Right? You can do this with 100,000 data rows maybe. If you hit 1 million, it's almost certainly going to fail. This is true for pretty much every database.
Cursor won't fail most of the time.
Yes, you have to start doing cursors. Cursors are expensive, they have state, they have timeouts, they have a bunch of different weird crap to do with them. So yeah, if your database supports cursors, which Couchbase doesn't, then you can probably do stuff with cursors, but generally speaking, this is not real time because you have to keep pulling, and also there's a ceiling of how much data you can bring in. But if you bring in not too much data, this works really well, much better than streaming everything all the time. Right? So if you run this, we should get the same rows we had earlier, obviously, because those are the only positive tweets in the database now. And there we go. Same ones, and you can see the mean sentiment. You can do all your nice Spark stuff on top. Yes.
If you want to do an aggregate, for example, best tweet every minute, then can you do it also in both ways?
If you want to do a sliding time window, actually, yeah, you can do it in both ways, right? It assumes that you have to read back at least 5 minutes of data. In this case, you can either start now and then you get the first result 5 minutes from now, or you can read everything and only keep the last 5 minutes if you need the old result. And with a query, yes, but then you actually obviously have to index the timestamp somehow so you can actually get it, because the query doesn't care when you run it. You know where date is now -5 or something, right? So also aggregate queries, in almost every database, aggregate queries are a painful topic, right? Because aggregations are hard, they don't scale very well. You have to do them all the time. Unless you're using a common database which is built for aggregations, every database that I talked about today will go scan the index, bring up all the results, and then basically count them in memory. Every time you run the query, it will count them again, because something always changes, right? Now, in Couchbase's case, it might push the count down to the index and save some performance, but it's not really designed for aggregations. It's a OLTP database, it's not an analytical database, right? But on the other hand, doing this thing in memory is just as bad, right? So if you can do it in real time, excellent. If not, there's a ceiling on just how much data, right? Then we're not talking about Hadoop here. This is still a database. It's big and scalable, but it's an order of magnitude less scalable in terms of data density than something like Hadoop or Spark on S3. Right? So, all right. So this is in terms of getting the data out. So let's talk very briefly before I finish about enriching data on the fly, right? And enriching data means, in almost every case, simply using the native database SDK in your streaming topology, right? In almost every case, it's going to be something Java or Scala-based, right? So you use this Java SDK, because who writes streaming applications in anything besides Java? Or Scala, sorry. Please.
People are running PySpark.
In production with like 1 billion events per day?
Billion, I don't know exactly, but I know people who are running PySpark.
I love Python. I'm not saying people don't run Python. I'm just saying not at the scales where it's actually interesting to talk about, okay, in terms of engineering, right? But okay, fine. I'm willing to assume that there are some crazy people doing Python as well. So you use the Python SDK to go and actually talk to the database. But you're talking to a distributed database, right? And as soon as you start talking about distributed databases, you introduce a bunch of different failure modes that you didn't have in your data streaming topology. We're actually just talking about that, right? What can you store in a database? There's basically two things. One, you can just store state, right? So a normal state, you can save your user, you bring in a user, you store whatever, a device ID or a session cookie, you save it, you bring it back. All you're asking from a database is just to be fast. That's all it needs to do. The other thing you can store is you can store the internal state of the streaming topology, right? So if it's Flink, you can store snapshots, for example, offsets instead of in RocksDB, maybe in an external database. If it's Storm, you can also store not much actually. Storm won't do anything. Sure. But as soon as you do that, you have to remember that databases have very different failure scenarios from data streaming platforms, right? Databases can have very odd partial failures. For example, what happens if you want to write a bunch of documents and one node in your cluster is down? So you succeed in writing 3 objects and you fail in the 4th, right? And this, you find yourself in this corner case where, is this a failure? Can you retry this? If you retry this, are you blocking the entire topology because you're still processing the same message and then all the other messages are waiting for you to finish the retries, right? So there are a lot of issues that come with the fact that databases are not entirely reliable, and so you have to start working around everything, right? So do you fail every message? If you fail a message, how do you go back to reprocess it? You start talking about dead letter queues. It's a whole big thing, right? I don't have time to go into it. There's like a day of workshops, but using your database as a side effect and topology is something most people don't really think through all the way, right? There are a lot of corner cases you have to consider if you're going to be breaking your delivery guarantees this way. So if at all possible, the ideal case for every data streaming topology is to have a pure functional topology in the middle and database as the source or database as the sink, and as much as possible to avoid having side effects. Obviously, it's not possible in every case. There are applications where you need to talk to the database and enrich it, but if it's possible to do it at the start of the streaming topology or at the end, it's usually less prone to failures and you can handle those failures much better than in the middle of your data stream. All right, so I'm done. Thank you very much.
One question if you
Yes, any questions or anything like that, please?
Thank you very much.